In the last class, we have seen the capacitance of a parallel plate capacitor with a dielectric slab in between them. And we have seen that the effective capacitance was given by C is equal to C0 divided by 1 minus T by D plus T by Kd, where T is the thickness of the dielectric slab. So now here we discuss a parallel plate capacitor with half the region between the plates is filled with the dielectric material and the other part is filled with air. So in this case we can see that T is equal to D by 2. So substituting here in this equation, the capacitance C is equal to C0 divided by 1 minus T by D is half. So 1 minus half plus T by Kd. T by D is half again. So 1 by 2K. So this can be written as C0 divided by 1 minus half is half, half plus 1 over 2K. So that is C0 divided by half into 1 plus 1 by K. So this half will go to the numerator and it will become 2 C0 divided by 1 plus 1 by K. So this 1 plus 1 by K can be written as 2 C0 divided by K plus 1 by K. So this is equal to 2K C0 divided by K plus 1. So we can find this capacitance of this combination in another method also. The half is filled with the dielectric material and the other half is filled with air. So now here we have a positive charge and a negative charge on this side. So this acts as two capacitors which are connected in series to a battery. So positive and negative. So this positive, negative. So this is negative and this is positive. So this acts as a series combination of two capacitors. So each having a distance between them d by 2. So for this combination, so let the capacitance is C1, this is C2. So for a series combination, we have seen that the effective capacitance C and C1 and C2 are related as 1 over C equal to 1 over C1 plus 1 over C2. For a series combination, the reciprocal of the effective capacitance is equal to the sum of the reciprocals of the individual capacitors. So now we can calculate C1. C1 is, there is a dielectric medium having dielectric constant K, epsilon 0 K, so both are having an area A, epsilon 0 K, A, and the distance between them is not D but D by 2, So 2 epsilon 0 K A by D. And C2 is another capacitor filled with air. So its capacitance is epsilon 0 A, K for air is 1 by D by 2. 2 epsilon 0 A by D. So this is 2 times K times C0. Where epsilon 0 A by D C0, the effective capacitance with air. So in terms of C0, we can write this as 2C0. Now we know that 1 over C equal to 1 over C1 plus 1 over C2. 1 over C1 is 1 over 2K C0 and 1 over C2 is 1 over 2C0. So we get, taking 2K C0 as a common factor, we get 1 by 2K C0. So now here we have to multiply numerator and denominator by 2K C0. So we get 1 plus K by 2K C0. So that is 1 over C. And therefore C is equal to 2K C0 divided by 1 plus K. So which is the same equation we have got here. 2K C0 by K plus 1. So you can use either of this method. So now we discuss a case where the region between the capacitor is half filled with the dielectric medium in such that the distance of each is d by 2. Area is being divided. So a region is divided into two. So one with the same distance between the plates is filled with the dielectric medium having dielectric constant K. And second one is filled with air. But here the distance is same. But the area is being divided A by 2 and A by 2. So what will happen? So in this case, the effective capacitance cannot be found using the equation we have studied before. So in this expression, this equation can be used when the separation distance is being divided. But here the area part is being divided between these two capacitors. So this is given a positive charge and this is given a negative charge. So we know that we have a capacitor here with positive and negative charge. So this is connected in such a way that the positive charge of the capacitor filled with the dielectric medium is connected to the positive charge of the capacitor filled with air. So these are connected. And the negative plate of the capacitor filled with dielectric medium is connected to the negative charge of the capacitor, charged plate of the capacitor filled with air. So this acts as a parallel combination with battery having positive and negative sign. So in this case, we have a series combination which is connected to a battery, positive and negative sides. So, but here we have a capacitors connected in parallel combination. So, the effective capacitance of the parallel combination is C equal to C1 plus C2. So, now we can find out C1 and C2. C1 equal to it's the capacitor which is filled with the dielectric medium. So, we have to multiply it by the dielectric constant K. K epsilon 0 instead of A, we have an area A by 2 divided by D. So, this is equal to K epsilon 0 A divided by 2D. But we know that epsilon 0 A by D is C0. So, K by 2 into C0. Now, we can find out the capacitance C2 which is filled with air. So, it is epsilon 0 since K is 1 and area is again A by 2 divided by D. So, epsilon 0 A by 2D. So, out of this epsilon 0 A by D is C0. So, it is C0 divided by 2. So now the effective capacitance in the parallel combination is just C1 plus C2. So which is equal to C1 plus C2 equal to C0 by 2 into K plus C0 by 2. So C0 by 2 is a common factor. So C0 by 2 into K plus 1. So we can see that in both cases the effective capacitance is not same. So they are different. So when the region between the capacitors is filled with a dielectric material such that the distance between them divides, then the expression for the capacitance is given by C equal to 2K C0 by 1 plus K. So generally 2K is greater than K plus 1 and therefore 2K by 1 plus K is greater than 1. So C0 multiplied by quantity is greater than C0. So C greater than C0, the effective capacitance increases. So in second case, for air, K plus 1 is equal to 2K is 1, K plus 1 by 2 is 1. So for all other media other than air is greater than 1 and therefore K plus 1 by 2 is greater than 1. So here also the capacitance increases. So by the introduction of a dielectric medium in between the capacitor plates, the capacitance always increases. But the percentage of increase is different, that depends on the how we introduce the dielectric medium, whether the distance between the plates is divided as in the first case, or the area between the plates is divided as in the second case. So anyway, the effective capacitance increases. Now we can do some problems. I will read the question. A spherical capacitor has an inner sphere of radius 12 cm and an outer sphere of radius 13 cm. So now the outer sphere is earthed. So this is having a radius 12 and this is having a radius 13. The outer one is earthed. And the inner sphere is given a charge of 2.5 microcoulomb plus 2.5 microcoulomb. So the space between the concentric spheres is filled with a liquid of dielectric constant 32. So this is filled with a sphere of dielectric constant 32. K is equal to 32 for the region between the concentric spheres. So now the question is that the first part is determine the capacitance of the capacitor. And the second part is what is the potential of the inner sphere. So we have to find out the capacitance of this spherical capacitor C and also the potential of the inner sphere V. So first of all, we can calculate this capacitance, and we have seen that the capacitance of a spherical capacitor is given by 4 pi epsilon 0 Ra Rb by Rb minus Ra when the dielectric medium in between them is air. So for that epsilon is epsilon 0. So for if there is another dielectric medium, so we have to replace this epsilon 0 by epsilon, where epsilon is equal to epsilon 0 into K or epsilon 0 into epsilon R. So we have just multiply. So this epsilon can be written as 4 pi epsilon 0 K Ra Rb by Rb minus Ra. So here Rb is equal to 0.13 meters, 13 centimeters, which is 0.13 meters in SI units. and RA is equal to 0.12 meters. And you can just find out the effective capacitance by substituting these values, and K here is 32. So we know that 4 pi epsilon 0, 1 over 4 pi epsilon 0 is 9 into 10 to the power 9, and therefore 4 pi epsilon 0 is 1 by 9 into 10 to the power 9. So substituting, you get the effective capacitance. So please complete this, and the answer is 5.5 into 10 to the power minus 9 farad. So that is 5.5 nanofarad. Now we have found the capacitance. Now the second part is, what is the potential of the inner sphere? The potential can be easily calculated as, we know that Q equal to CV, and therefore V is equal to Q by C. So the charge given is 2.5 microcoulomb, that is 2.5 into 10 to the power minus 6 coulombs divided by the capacitance. So this is the capacitance in SI units. So 5.5 into 10 to the power minus 9. And please calculate, and the result is found to be 4.5 into 10 to the power 2 volt. Now the next problem is that a sphere of 4 centimeter radius is suspended within a hollow sphere of 6 centimeter radius. So we have a sphere of 4 centimeter radius, and which is inside a sphere of radius 6 centimeter. So the inner sphere is charged with a potential 900 volt when the outer sphere is earthed. So find out the charge on the inner sphere. So suppose the charge given is Q on the inner sphere, minus Q is induced on the inner side of the outer sphere, and this part is earthed. So we have seen this in the principle of the spherical capacitor, and we have seen that in the case of the spherical capacitor, the potential difference is equal to VA minus VB, which is Q by 4 pi epsilon 0 RA, the radius of the inner sphere, and the outer sphere is having a charge minus Q by 4 pi epsilon 0 RP. So that is Q by 4 pi epsilon 0 into 1 over RA minus 1 over RB. So RA and RB are given. So substituting those values, and the potential V is also given, 900 volt. So from this equation you can find the charge. So please calculate this charge. So this is an assignment for you. The next question is that two small drops, each having a charge Q and a potential V, are combined to form a bigger drop. Find the potential of the bigger drop. So here two equivalent drops coalesces into a bigger drop. So we have to calculate the potential of this bigger drop. V of the drop, Vd. So this is our question, and we can see that while coalescing, the total charge add. So the charge of the bigger drop, capital Q, is equal to Q plus Q, 2Q. So while coalescing, we know that the radius will not be the sum of those two radius. So what is being added is that the volume. The volume of those two drops is equal to the volume of the bigger drop. So we can suppose small r is the radius of the drop, initial drops, and capital R is the radius of the resultant drop. So we have to calculate capital R. Small r is given. So once the potential and charge are given, you can easily find out small r. So now we have to calculate capital R in terms of small r. So for that the volume adds. So volume of the first sphere is 4 by 3 pi small r cube, and the second one is also having the same volume, which is equal to 4 by 3 pi capital R cube. So the 4 by 3's will get cancelled. 2 into r small r cube is equal to capital R cube. So taking cube roots on both sides, capital R is equal to 2r cube raised to 1 by 3. So that is 2 raised to 1 by 3 r. So the radius of the drop is equal to 2 to the power 1 by 3 raised to r. So the corresponding potential is q by 4 pi, capital Q by 4 pi epsilon 0 r. The capital V is here. So capital Q is 2 into small q. The charge adds, and 4 pi epsilon 0. Capital R is 2 raised to 1 by 3 small r. So 2 divided by 2 raised to 1 by 3 into 4 q divided by 4 pi epsilon 0 r. So this is the initial potential, which is small v. So this is the capital V of the drop, final drop, or we can use the capital letters to represent the bigger drop. So 2 divided by 2 raised to 1 by 3 into small v. So 2 divided by 2 raised to 1 by 3 is 2 to the power 1 minus 2 to the power 1 by 3. So 2 to the power 2 by 3 into the potential of the initial drops. So now we have to calculate the potential of the effective drop when there are n small drops to combine. So suppose n small drops combine to form a bigger drop. So in that case, the potential have to be calculated. So V equal to capital V. So we have n small drops, each having potential V and charge small q and radius r. And we know that capital Q is n times q, q plus q n times, and the volume is conserved. So if there are n drops, then 4 by 3 pi r cube plus 4 by 3 pi r cube n times is equal to 4 by 3 pi capital R cube. So that is, this is added n times, that is n into 4 by 3 pi small r cube is equal to 4 by 3 pi capital R cube. So we have capital R cube is equal to n into small r cube. So taking cube roots on both sides, we get r is equal to n to the power 1 by 3 r, and the corresponding potential of the larger drop is equal to 1 by 4 pi epsilon 0 q, capital Q by capital R. Q is nq and r is n raised to 1 by 3 r. So we have n divided by n to the power 1 by 3 q by 4 pi epsilon 0 r. So this is the small v. So n divided by n to the power 1 by 3 is n to the power 2 by 3 into v. So you can calculate the effective potential if the number of drops and the potential of each drop are given. So in the textbook, the problem is given 64 small drops each having a potential 10 volts are combined to a bigger drop. Find the potential of the bigger drop. So in that case, N is 64 and V is 10 volt. And please do the problem. That is an assignment for you. So when equivalent drops, charged equivalent drops combine to form a single drop, we have to note that the total charge on the final drop is equal to the sum of the charges of the individual drops, and the volume is being conserved. That means the volume before the process is equal to volume after the process.